What are properties? When we say properties of something, what do we mean properties? What do they represent?
I guess something that you own, like a substance.
That's chattel. That's one type of property, but not this type of property. Like, the property of rational functions is not a land of rational functions. But no,
Rules.
rules. Yeah, that's the best way to say it is rules. These describe what we cannot do, what's supposed to happen, what's not supposed to happen. So here we're talking about what are rational functions. Rational means what? Yeah, a ratio or fractions. So these are talking about rational functions or fractions, polynomial fractions. And they look like this. So any rational function is going to be made up of a polynomial on top and a polynomial on the bottom. What is a polynomial? Polynomial is simply a number with many terms. It can have one term, it can have two terms, it can have 1,000 terms. So P and Q are both polynomials. What's the domain of rational functions? What do you think would define the domain of a rational function? Yes,
QX or where Q of X does not equal 0. Since
that's it's an important thing, yes. But there's one other thing what about the numerator? In general, the algebra of polynomial rational functions. In other words, or actually, not just rational, but just polynomial functions. What that means is the addition, subtraction, multiplication, and division of polynomials. You can combine polynomial equations by adding them together, subtracting them, multiplying, or dividing. The domain of the algebra of polynomial functions, in other words, the domain when you add them, subtract them, multiply, and divide. The intersection of their respective domains. What does that mean? So the domain of f of x, or the p of x, and the domain of q of x, whatever those are, the overlapping of those, where they overlap, that's your domain. For example, if the domain of p of x was -2 to 5, and the domain of q of x was -infinity to +infinity, then a domain of P and Q, or plus minus whatever, is where they overlap. Because think of it. If you're adding and subtracting or multiplying polynomial equations, and one of them, you enter a number that's outside the domain, what happens to the whole equation? In other words, can I add if Q of X is the square root of X plus 1, can I put that in there? No. So again, it's only overlapping where the smallest domain is defined. Does that make sense? But I'm hoping. So it's wherever the two functions overlap in the domain, that's where the domain of your algebra is. So, except when it comes to rational expressions, it's overlapping plus where Q of X does not equal 0. Remember, the bottom can never equal 0. But it's the both. It's the overlapping of the two domains and wherever the denominator is not equal to 0. Not just 0, but it has to be defined. So let's look at some examples here. X squared minus 4x plus 5. Tell me the domain of this function. What's the domain of the top? What kind of equation is it?
It's all real numbers.
It's quadratic. It's a parabola, so it's all real numbers. So the top, the domain is negative infinity to positive infinity. How about the bottom? It's a linear equation. So what is its domain? Negative infinity to positive infinity. I'm looking at each of these separately to begin with. Not yet, because it's a two-part process. You have to first find where they overlap. Because if this thing here was a square root, it's not just one number, it's a whole series of numbers. So since they're infinity, negative infinity, so far our domain for this rational expression is that, so far. Except x plus 5 cannot equal 0. So in other words, x cannot equal negative 5. So our domain is from negative infinity to negative 5, unioned negative 5 to positive infinity. That's how you figure out the domains of these things. So you say that x is not equal to negative 5, because that's the only restriction we have on it. Our rational function is 1 over x squared minus 4. What is its domain? So what's the domain of the numerator?
1.
It's 1. It's a horizontal line. So the domain is negative infinity, positive infinity. So what's the domain on the bottom?
Negative infinity, positive infinity.
Yeah, it's a quadratic equation. So far we're going from negative infinity, positive infinity. It's the same on top and bottom. Now we gotta take the bottom, set it equal to 0. And if we square root both sides, what do we get? No,
Plus or minus.
plus or minus 2. So x cannot equal plus or minus 2. That's our domain. Or we could say that it's negative infinity to negative 2, negative 2 to 2, 2 to positive infinity. You have to be able to represent it both ways, as an interval or as just if it's just a single set of numbers. Yes.
Then we got. So I know we have. Parentheses, which is up to, and then
Yes.
brackets are.
Bracket.
If we run into that. if we Get an equal.
No, because we're looking for restrictions on the bottom. It's at these numbers, it cannot equal those, so it has to be a parenthesis. If we use a bracket, then we can use it, and then that would be it.
Okay, can use that.
Yeah, so the bracket is inclusive. Parentheses is exclude.
If you get infinitely close to -2, but.
Yes, infinitely close. Yes, yes, yes. And that's going to be an important concept when you get to calculus, because even though the function doesn't exist there, we can get infinitely close to it, and it may approach a value. What about number 3? X cubed over x squared plus 1. What's the domain of the numerator? Which look at them separately, not as a fraction.
Sorry, no, x cubed is that kind of graph.
Yeah, it's this one.
Mhm.
How about the bottom one?
Negative infinity, positive infinity.
So the domain so far looks like negative infinity to positive infinity. Are there any restrictions on the bottom? Because it's squared. Yeah, so if you look at this, if you set this equal to 0, you can't have that. A squared term can never equal negative number. So there's no restriction. That's our domain. So far, so good?
Oh, I actually have a question.
Yes.
So I noticed in example 1, compared to example 2, where we did the I guess like x plus 5, it couldn't equal 0, but x squared minus 4
Well, we set it equal to 0 and then solve for x. So this is where it cannot, those are my restrictions.
Okay,
And that's what I said here. So x cannot equal plus or minus 2.
but how do we know that x plus 5 can't equal 0? For example 1.
This one here,
Yeah.
because we cannot have 0 on the bottom. So we set that
Oh.
equals 0, and anything that makes the bottom equal 0, we can't use.
Okay.
And that's why we go parenthesis there.
Okay.
Okay, now this one's going to be interesting. X squared minus 1, x minus 1. What's the domain of the top? Yeah, because it's a parabola. How about the bottom? It's a linear equation, so it's negative infinity, positive infinity. So far, our domain of our function is negative infinity to positive infinity, because that's the way both of them are. Now we have to check the bottom. Set it equal to 0. So that's the only value we cannot use. So the domain on the bottom is x cannot equal 1, or you can say from negative infinity to 1, union 1 to infinity. Give you another one. I'll make this one up.
That's the V.
Absolute value. V is the absolute value.
Yeah, that's right.
What's that? So what's the domain on the top? Which one? Nope. -1 to infinity. Because we set the, whatever's inside there, set it equal to 0, we get -1. How about the bottom? Oh. Where's the bottom going? Why is it from -infinity to 2? Let's look at this function. First off, from the library of function, what function is it? Square root of x. What's the graph look like? It starts at 0 and it goes like this. Again, memorize library of functions. The second transformation here is the sign of x changes. Since it's inside the function, and you change the sign of x, what does that do to the graph? Doesn't move it. Across what? Yes, so now it goes this way. Because we have to get rid of that negative sign by putting negative numbers in there.
Not only that though, like if you were to set the denominator to 0, because it's a square root, then it becomes an inequality, right? Because 2 minus
Well,
x.
if you just set the bottom equals 0, then you get x equals 2. So that's one of our things is x cannot equal 2.
No, I mean, but don't you, when you wouldn't set it equal, you would set it greater than or equal to like 0, and then if you algebraically.
That's the transformation you do is you work backwards from the function itself. You don't set it to anything. You just said, look at what is the function telling us? The only thing you set equal to anything is you take whatever's inside there, set it equal to 0, because that's the smallest it could ever be in there. Because in a radical, the smallest you can have is 0. It can't be negative. It can only be 0 or positive. So we set it equal to 0 and solve for x. So now look at our transformation here. 2 minus x. What this did for us, it moved to the right 2 spaces. And it goes like this. So the bottom is from -infinity to 2. And I cannot use 2, so it's bracket. So if we look at these two domains, we go from -1 to infinity. And the bottom is from -infinity to 2. So this is the numerator, this is the denominator. So where these two graphs overlap, that's the domain of my function. That's the domain of my function. It could only be where they both overlap. Make sense? Yeah. All right. If anybody's still writing, tell me, I'll put it back up. What does that graph look like? And what's my domain?
So the main on top is
No.
negative infinity, positive infinity.
Yes.
The bottom is negative infinity, positive infinity as well.
Nope. Can you set it equal to 0?
Oh, no, you can't.
So it can't, x cannot equal 0. So it's a vertical asymptote. The graph of this one, it can never be negative. If I put a negative number in there and I square it, it becomes positive. So it's the Atari symbol. So what's my domain? Since it has a vertical asymptote where I set it equal to 0, so x cannot equal 0. That is your vertical asymptote. So you see how we're putting all this stuff algebraic together? The restrictions on our domain of rational function is anywhere there's a vertical asymptote. Vertical asymptote is anywhere that there's 0 on the bottom. All this stuff now starts being put together.
Super confused.
At what?
Well, I don't understand what we're doing different compared to like what we did in the first section of this course where we had like in 2.1 where we had rational functions and we would find the domain of them.
They were just rational, just from the library of functions. Now we're gonna start building up for different polynomials. We have multiple, because what if I gave you a function like this?
Okay.
If I gave you a function like that, what's my domain there? Because now we're looking at polynomials. We're building up to that point. So actually, okay, what would be my domain here? Since you opened that bag of worms. No, because if you look at the stuff we did earlier, we talked about the basic ideas, which builds from that, we build up to here. So what's the domain of the numerator? It's a quadratic equation. Look at the leading term. It tells you what it is. How about the bottom? What's the domain of that one? It's also a quadratic, so it's from negative infinity to infinity. But now we have to look at a little bit further where it equals 0. The only way we can do that is by factoring it now. We have to find the exact values where it equals 0. So what makes x squared? X and x. They both have to have the same sign. They're both minuses. What times what is 12? When you add them, you get 7. So x cannot equal positive 4 and positive 3. So that's my domain. It's from negative infinity to 3. 3 to 4, 4 to infinity. That's my domain. Or, I say that. So we're just building up from there. And also we're gonna look at transformations. How do they, if they have anything to do with it.
If I forgot, like, in what instances. With either from the denominator or the numerator, where you look to find the domain from. So I guess.
You're looking for both. You have to look at from both
Alright,
because
I guess.
and again, you have to look from both, because what if we had a radical up on top? What if we had a radical on top?
Yeah, then you would.
Now now this one has a restriction, so we have to find its own domain. In the bottom, we have its domain with these. And then wherever those two overlap, that's our final domain. So that's what we have to look at the top and the bottom and then see where their actual domains overlap. That's what our final answer is going to be.
So without the radical.
Without the radical, then this would be our domain. That's the only restrictions we have is at the asymptotes. Because we can't have the bottom equal to 0. So yeah, it's not just one thing you look at. You have to look at both numerator and denominator. That's why we look at the first thing I do is look at the domain at top and bottom, and then look for any restrictions on the bottom. X minus 2 squared plus 1. What's that one going to look like? Graph this one and tell me the restrictions, the domain. Well, actually, I want you to do things. I want you to graph it. I want you to tell me the domain and the range. Because once you graph it, you can tell me domain and range just from the graph. Pretty much in this section, we're going to define asymptotes, horizontal and vertical and oblique. Let's graph it first. First off, let's look at the whole thing. What function do we have there? 1 over x squared. Because it's squared. So what does that graph look like? The Atari symbol. Then the second thing we look at, is there a horizontal shift? What's happening inside the function? So what does that tell me to do? Yeah, it's always the opposite. So set that equal to 0. So x equals 2. So there's my new. So it looks like this now. So 2 is my vertical asymptote. x equals 2. Because that's where it's undefined. What's the third transformation? We have 1 over x minus 2 squared plus 1. The plus 1 is happening outside the function. If it's happening outside of the function, what does that mean? It's a vertical shift. So we go 2 to the right, and then this one says go up 1. So there's my new xy. This is my new origin. The graph looks like this. So what's the domain? And then, right, negative infinity to 2, 2 to positive infinity, or you can simply say x does not equal to 2. Either one will work. What's my range? Well, it has to have a range. It's the y values. Where? Is there any graph down here? So it can't be in the negatives.
This would be a positive, +1.
Yeah, so the range could be y is greater than 1, because it never equals 1. Or you can say that it's 1 to positive infinity. So what does this tell us? What are we looking at here? Other ways of looking at this. This line here is my horizontal asymptote. This line here is my vertical. What are asymptotes?
It's the lines that intersect with the y or x axis.
A line that the function cannot cross. That's the vertical asymptote. Or can only approach. Like the horizontal asymptote. In other words, the horizontal asymptotes, the graph can cross the horizontal asymptote, but as soon as it crosses it, it has to taper down back to getting close to it. It never stops at it, it just approaches to it infinitely. So now let's look at how do we find these things. Let's see how we find asymptotes, horizontal and vertical. We're going to look at the simple function 1 over x. We know the graph looks like this. So let's look at what is the vertical asymptote here in this equation? X equals 0 is the vertical asymptote. It's where the function's undefined. What's the horizontal asymptote? Very good, very good. Y equals 0 because it's a horizontal line. It's crossing the y-axis. So let's look what happens here with the values of X. What we're looking at here, since this is a vertical asymptote, as X approaches 0 from the left, that's how you read this. As X approaches 0 from the left, blah, blah, blah. So as X approaches 0 from the left, what happens to our Y values? Where's our graph going? To where? Y goes to negative infinity. Right. Then, as X goes to 0 from the right, what happens? As X approaches 0 from the right, what happens? Where's the Y value going? Y value is going to positive infinity. Okay, so now let's look at the horizontal asymptotes. For these, as X goes to infinity, as X goes to infinity, where's the Y value going? As X goes to negative infinity, as X goes to negative infinity, Y is going also to 0. These are important concepts because you notice, where is X going? In this case, the vertical asymptote is 0. If the vertical asymptote wasn't 0, let's say it was 5, then I'd go to 5. Go 5 from the left to the right. So a vertical asymptote, as our X value approaches some number A, whatever that vertical asymptote is, Y goes to positive or negative infinity. That's a vertical asymptote. Now here, the horizontal asymptote, as X approaches positive or negative infinity, Y approaches some value B. Does the x-axis always have to be the horizontal asymptote? No, we just proved that it didn't have to because of this one right here. Let's look at what happened with the last one. One over x plus or x minus 2 squared plus 1. This is supposed to be a minus. So what's our restriction of our domain? What x can we not use? Yeah, so we take x minus 2 set equals 0. This is my A value. So as I get closer and closer and closer to 2, where's my graph going? As my x approaches 2 from the left, where's this graph going? positive infinity. As x approaches 2 from the right, where is it approaching since it's a squared term? It's also a positive infinity. So because I'm going to some value and it's going to positive or negative, that means x equals 2 is my vertical asymptote. Because at 2, it makes it go to positive, negative infinity. So this is the vertical asymptote. Let's look at the horizontal asymptote. As x goes to positive infinity, what happens to this function when x goes to positive infinity? As x gets bigger, 10 minus 2 squared is 64. 12 minus 2 squared is 100, which was 1 over 100. 1000 minus 2 squared is 1 over what? So what happens to this number as x gets bigger and bigger and bigger? Yeah. 1 over x, as x gets bigger, this number gets smaller and smaller and smaller and goes to where? 0. So as x goes to infinity, this number goes to where? And then we're left with 1. So my y value is 1. That's my horizontal asymptote. As x goes to negative infinity, again, this number here, no matter what it is, when I square it, it becomes positive, so it gets smaller and smaller and smaller. Eventually that goes to 0. So y equals 1 is my horizontal asymptote. And we're going to look at these things. So basically, if we're taking x going to a special value and it goes to infinity or negative infinity, then that's a vertical asymptote. If we go to x to positive or negative infinity, then we're looking for the horizontal asymptotes, because the horizontal asymptotes go out to infinity and h comes down. And there are shortcuts too, we'll get to in a second. This is the stuff we've done already. So let's see if we could go through this pretty quick. Originally, they're asking you only for the vertical asymptote. But I'm going to say let's go for both. Tell me the horizontal and the vertical asymptote. The horizontal and the vertical asymptote of each of these, if possible. Because we haven't formally defined them yet. So that's what we'll look at in a second. Let's look at the horizontal asymptotes, or vertical asymptotes first. In this A, what's the vertical asymptote for A?
1,
Mm-hmm. Because that's what makes it equal to 0. How about the next one?
that would be 2.
Nope, plus or minus 2.
Oh, yeah.
Because, see, how about the next, the C? What's that?
It can't be negative 1. No.
So what's the vertical asymptote? Doesn't
Oh,
have
it
one,
does not.
because you can't make the bottom equal to 0. Okay, D will have to do some work. On the top, x squared plus 9, what does that factor out into? Very good. What's that called? The difference of 2 squares, because this is the same thing as x squared minus 3 squared. Very good. So it's because it's a minus between there and they're both squared, it's x plus 3, x minus 3. Now the bottom number, since the second sign's a minus, that means they have the opposite signs. And the bigger number gets a positive, right? It has to be 7 and 3. 7 goes to the positive.
Explain that again.
Because look at the signs. Since the second sign, the only way that could be negative is if multiplying 2 opposite signs. The only way it could be positive is if you take 7 minus 3, it has to be positive. So the second sign tells you what the signs are. If it's a minus, they're opposite. The bigger number gets that sign.
Okay.
If it's a plus, that means they're the same signs. It's whatever the first sign is. So if that's a plus and that's a minus, that means it's a minus minus.
Yeah.
I'll write it down for you in a little bit. If you want me to. Okay, so what do we do for this? Those cancel. So my is 3 a vertical asymptote? What is it? So what's the difference between an asymptote and a hole?
Where something cancels out as a whole, and then that asymptote is where creating the undefined.
Yes, but how will we define vertical asymptotes a second ago? As x goes to a, where does the function go? Now, if I plug it into 3, if it's a hole, does it go to infinity? No. A hole is not the same as an asymptote, because an asymptote, like that's -7, at this line here, the graph is going to go either to positive or negative infinity as we approach it. That's an asymptote. At 3, whatever value that is, it's just a hole. So the difference is, as x approaches 3 in this case, it's going to be whatever the value is that's supposed to be there, that it's approaching. But an asymptote, it goes either plus or minus infinity. Those are the differences between holes and asymptotes. So this is what we call a removable discontinuity, a hole. Now, this is the graph that we look at. So here, our vertical asymptote is at x equals -7. Because that's the only one that's going to give us an asymptote. Now, for horizontal asymptotes, what do you remember from algebra? Horizontal asymptotes. You said you were finished. Where'd you get that from? What? How about this one? 0. How about this one? How about this one? What? Horizontal asymptotes. Let's look at that first. Okay, so everybody's okay with vertical asymptotes. It's where the bottom goes to 0 or goes to infinity by it's a value that goes to 0. The vertical asymptote, the horizontal asymptotes is a different animal. First off, we have to look at the function y1 over x. Because remember we talked about earlier, to test horizontal asymptotes, we go to positive and negative infinity. So here, as x goes to infinity, where does this equation go to? As x gets bigger and bigger and bigger, what does y go to? The value of y go to? It goes to 0 because it gets small. It starts off at 1 over 1, 1/2, 1/10, 1/100th, 1/1000th. It gets smaller and smaller, smaller. Eventually, it goes to 0. It gets so small, infinitely small, it gets close to 0. So notice there's more x's on the bottom than the top. That's the thing that you're looking for. What happens if we have this function? As x goes to infinity, where does y go to? Infinity. Just a lot faster because it's squared. So any polynomial or say rational function is made up of polynomials. And the bottom will make it Bn. Make it M, make it a different letter so we don't get confused. So it's AN on top, BM on the bottom. When we look at polynomials, what is the most powerful part of those polynomials? Which one? Of which number? What's that first one called? Leading is correct. Yeah, so actually, all this other stuff is irrelevant. All it's going to tell us is where the y-intercept is, and we have to now worry about the rest of that stuff figured out. So whenever we look at rational expressions, what these are called, they're called the leading terms. The leading terms are the first term, the terms of a polynomial that have the highest exponent, because they create more change to that polynomial than anything else. So for the horizontal asymptotes, all we have to look at are the exponents of the leading terms. If the top exponent is bigger than the bottom exponent of the leading term, what does that mean? That means there's more x's on top than the bottom. So if I had an equation 2 over 3x and as x goes to infinity, where does this go? As when X is 1, we get 2/3. When X is 2, we get 4/3. When X is 3, we get 6/3. What's happening to the numbers?
Extended.
They're getting bigger and bigger. So if there's more X's on top than the bottom, then it doesn't exist because it goes to infinity. It goes to positive and negative infinity. It either goes up or it goes down forever, and we can't control it. That's if the top is bigger than the bottom. If the top is smaller than the bottom, we're talking about the exponents. As X goes to infinity, where does this one go to? So if the exponent on the bottom is bigger than the exponent on top, it's why the horizontal axis is 0. It's the line y equals 0. It's the x-axis. What if they're equal? You'll see why it's 1. Because here we have on top, let's say it's 3, and the bottom, let's say it's 3. What happens to the x values there? They cancel. So we're only left with the coefficient a over b. So you see why it's 1, because the coefficients of those examples were 1 and 1.
I remember learning this now.
Yeah, many years ago. Before batteries, before electricity. No, eventually you're gonna learn nothing. You remember a whole bunch, which you've seen this stuff before.
Like I'm reading it in my head, you know.
I have specific notes on all this stuff right here, like, as you're doing it, I'm like. my notes are coming.
Flashbacks.
Yeah.
So those cheap kung fu
I
movies.
remember I wrote that down.
So yeah, so we see in our examples over here, the leading terms. I forget about that. I don't need that anymore. So it's x over x. So it's just a coefficient. 1 over 1 is 1. This one has more on the bottom than the top. So it goes to 0. Because 1 over x goes to 0. They're both x squared, so they cancel. So it's 1 over 1. X squared, they're both 1 over 1. So that's how it works. Make sense? Yes. All right, so now let's look at multiplicity and vertical asymptotes. Okay, we know what vertical asymptotes are. That's the x values that make what? What? The bottom makes the function undefined, makes the bottom equal to 0. What is a multiplicity? You can say that. Multiplicity, it started off in polynomials. If we had a polynomial and we factored it out, what's the degree of this polynomial?
3.
Nope.
Oh, yeah, 'cause
11.
it's
Why?
you're adding.
You're adding up all of these exponents. These are the multiplicities. How many times the 0 repeats itself? So if we add up all those. Now, what is the importance? Why does knowing the degree help us? with our graphs.
For balances or crosses?
That's multiplicities. No. Okay, so let's go ahead and sketch this graph real quick. What do we know about the intercepts here? What are my solutions? Yeah, take each of these, set them equal to 0. So it's 0. This one makes it -3. This one makes it 4. This one makes it 5. And this one makes it -6. So I take each of these, set them equal to 0 and solve them. Those are my solutions. Those are my x-intercepts. Same thing. X-intercepts, solutions, factors, zeros.
The degree tells you where the graph crosses or bounces off the.
Multiplicity does that. The degree tells us the end behavior. Since the degree is 11, what do we know about the end behavior of the graph?
Correct.
Yes. So one goes up and one goes down from the last intercepts. Because all of the x's are positive, so we know it's that. If this one is negative, then it'd go the opposite direction. All right, so at -6, this one, does it bounce or cross? Bounces because it's even. Actually, we know, we've seen this before. What does the graph of x squared look like? What does the graph of x cubed look like? So if the multiplicity is even, it bounces. If it's odd, it goes through. So at -6, the multiplicity was 2. At -3, it's 3, so it crosses. At 0, it's 2, so what does it do? It bounces. At 4, it's 1, so it crosses. And at 5, it's 3, so it crosses. So this is a rough idea what the graph looks like. Simply by using the multiplicities of our factors. So that's what we learn in algebra, how to graph, how it helps our graph. So the multiplicity tells us that. With respect to our vertical asymptotes, so what's going to happen here? Because remember, these are multiplicities with respect to our vertical asymptotes. So what's going to happen here? How are these going to change what happens to our graph? What is this graph going to look like? ¿Por qué no? Why is it not the Atari symbol? It's not squared. So we know this one, we know the shift is where? 2 to the right. There's no vertical shift, so that's our graph. How about R2? What's the difference between R1 and R2? Across where? No. Because this is happening outside the function. This is the function right here, 1 over x. This is the same thing as 1 over x minus 2. If it happens outside, it reflects across where? The x-axis. It goes from positive, so since all these are negative, and if all these are negative, let's see here, all these are negative, and I change the sign of them, they now become positive. If all these are positive on this side, and I change the sign, they're now negative. How about these last two? What is this one going to look like? Now you can say the answer. Sorry, simple. Yes, very good. R3 is an Atari symbol. It's shifted to the right 2 spaces. And then R4, because it was negative 1 over x minus 2 squared. Now this one, because I reflect it now, it goes down. So what did the multiplicities do for our graphs? It either makes them go the same direction or not. If the degree is even for vertical asymptote, it goes the same direction. If it's odd, it goes opposite directions. So that's what the that's what the multiplicity tells us with respect to our degrees. There's always the exception to the rule. Remember, horizontal asymptotes. If n was bigger than m, if n was less than m, if n was equal to m, remember we had a x to the n, b x to the m. So what would this horizontal asymptote be?
Doesn't have one.
Yeah, it goes to infinity, so it doesn't exist. Because the top is bigger than the bottom. How about if the top is smaller than the bottom? 0. Because if there's more x's on the bottom, then it gets smaller and smaller, it goes to 0. If they're equal, a over b. You're never gonna forget that one.
That equals 1.
No, it's just whatever a over b is. Because it just so happened that all our examples were 1s. But if there were 2 over 3 or -7 over whatever, it's just a over the coefficients, leading coefficients. Except with this one. Put your cell phone away. You don't need it that much. Put it away. Except if the bottom is bigger than the bottom by 1.
Wait, so.
So if we had two x to the fifth over three x to the fourth. According to our old rule, the top is bigger than the bottom, so it goes to infinity. What happens when we simplify these? How many cancels? 4 of these and 4 of those, this leaves me with 1. So I have 2x over 3. This is a linear equation, which is an oblique. So if the top is bigger than the bottom by 1, we have an oblique asymptote. A line. In this case, since there's no vertical shift, the crosses the y-intercept is 0 up to over 3. Let me give you an example. So the rational expression, actually, maybe they have one here for us. Here one. Here's 2 of them for us. You tell me which one's which. We're looking for the horizontal asymptote. 4x3, 5x plus 2, 7x5, 2x4. So what's the horizontal asymptote?
0.
Why?
Because the top one is smaller than the.
Right,
bottom.
because there's more of them on the bottom. So how would you graph that? The horizontal asymptote being 0. Yes, it's but where? Yeah, so this is simply another way of saying y equals 0. The horizontal asymptote is simply the y value. So like when we had the a over b, it's y equals a over b, whatever that y value is, that's a horizontal asymptote. That's where it goes through. Example 6. How about this one? H of x is equal to 3x to the 4 minus x squared, x cubed minus x squared plus 1. What's the horizontal asymptote?
It's an oblique.
Yeah, so does not exist. It's an oblique asymptote. Because horizontal asymptote says if there's more on top than the bottom, it doesn't exist. It becomes an oblique asymptote. So what is the oblique asymptote in this case? How do you find it? To find an oblique asymptote, use long division. Remember what that was? Okay. No, it's an honest answer. So if we had 8 over 5, we can rewrite that as 5 goes into 8. How many times 5 go into 8? Then what do you do after that? 1 times 5 is 5. Then what? Subtract. So your answer here is 1, 3 over 5. This is long division right here. I know it's it sort of stops being fun. It's a lot more fun if it's a synthetic division, but we have to use long division here. So take the bottom number.
Oh, I think I remember. You gotta, you have to put in, the degrees have to gradually.
You have to line them up, right? So once you get them lined up and you fill in all the spaces, look at the leading terms. What times x cubed gives me 3x to the fourth? Three x, very good. I need one more x. I need a 3. So 3x times x cubed is 3x to the fourth. 3x times negative x squared is negative 3x cubed. Three x times 1 is positive 3x. Now we gotta change the signs. We have to subtract. So the first term should cancel. 3x cubed x squared minus 3x. Repeat the process. What times x cubed gives me 3x cubed? A positive 3. The signs are important here. So positive 3 times x cubed is 3x cubed. Positive 3 times negative 2x is negative 3x squared. Positive 3 times 1 is positive 3. Change the signs. Four x squared x. Once you have a linear equation, you're done. We don't care about the rest of this stuff because this is a linear equation. You can only have a y, an mx plus b. You have so in this case, our oblique asymptote is the line 3x plus 3. First, what does this number represent?
The y-intercept.
The y-intercept. So always start off with that and then follow the slope. Rise, go up 3, 1, 2, 3 over 1. And there's your oblique asymptote. That's long division. And then we have to find the vertical asymptote. And now it's a cubic one. That'll be a lot more work because we have to go through the whole process of finding all the rational zeros and then do the synthetic division, find out which ones are the actual zeros. We'd get 3 of them. So, or we get 1 real one and 2 artificial ones. But all we're supposed to find there is the oblique asymptote. All right, we have this example. Tell me whether it's an oblique or a horizontal asymptote, and then find it for me. So is it oblique or horizontal?
Horizontal,
Why?
8/4.
Why should it
Because
be?
they're equal, the two exponents. are
Yeah,
equal
the
to each other.
only way it would be oblique is if what?
If top is one, yeah.
Yeah. If the top was one bigger than the bottom, since they're equal, that means it's a horizontal asymptote. Two. This one? This doesn't matter that. You only for oblique for these asymptotes, only look at the leading terms. So since they're x squared over x squared, they cancel. So the horizontal asymptote is on the line y equals 2.
If it was x or 8x to the power 4 and 4x to the power 2.
Ooh, did y'all hear that? Here's a hypothetical. What if it was 8x to the power 4 and 4x to the power 2? Is it oblique? No, because that's not one bigger than this one. So it's got to be horizontal. If I simplify these, there's x squares on top. As x goes to infinity, this one goes to infinity. So it doesn't exist. It doesn't have a horizontal asymptote. So nothing exists there. Good question, though. Yeah, so you look at the leading term, and if the top is bigger than the bottom, unless it's by 1, then it doesn't exist. G of x. I'm gonna change the number a little bit. Is it horizontal or oblique?
So,
It's oblique. So long division, your heart's out.
oh man. What gets me is switching the signs.
At the very after you multiply them,
Yeah, I'm like,
because think if the leading terms don't cancel, then you do something wrong. Each term, the leading term is supposed to cancel. That's why you change the signs.
okay. Go 0 to the second power. You go 0 to 1, or is it just 0? Your last term.
This one here. This will have 0x squared, 0x, and just leave that one as a constant.
That's right. Never mind.
Never mind. I got it.
0.
Good.
I don't remember how to do this. I mean, I just watched you do it.
Need about 3 more minutes.
Let's see.
We have to first set it up this way. If you didn't set it up this way, you can't go any further
Why is it +2?
because it's +2 there. So I'm just missing the x squared and x. I'll put those in there. Yeah, so setting up is the very first. If you get that wrong, the whole thing's wrong.
The signs, so that I can like a subtraction problem.
Right.
So you're just trying to get zeros all the way across. Huh?
Well, you actually you're only gonna do this twice because for a linear equation you have to have a mx plus b.
You have to minus that.
Let's see, yeah. So what's the first step? what times x cubed give me two x to the fourth?
2x.
Two x. So two x times x cubed is two x to the fourth. Two x times negative one is negative two x. Change the signs and add. So we have negative x cubed, 0x squared, plus 2x plus 2. Repeat the process. What times x cubed gives me negative x cubed? Negative 1. So negative 1 x cubed is negative x cubed. Negative negative is a positive 1. Change the signs. And that's our oblique asymptote. 2x minus 1.
Where does the x squared go?
Which one?
Like in the very
This one?
bottom. Yeah, where does that one go?
It's 0. It doesn't go anywhere.
Oh.
I don't need it
so
anymore
you don't-
since that's a 0, it doesn't exist. There's 2x.
Oh, so it's not gonna be x squared plus.
It'd be 0x squared, but 0
Oh.
x squared is nothing. But then I don't need it because once you get 2 steps done, I don't care what's left. And because this number will never fit whatever's left. So that's what you're looking for at that point.
This, like, finding oblique asymptotes, was that part of algebra? I don't remember doing.
Yeah, it's
I remember doing, this like long division, but for some reason I thought it was for finding something else.
to find the solutions to polynomials. Yeah, once we found the rational zeros, then we had to use synthetic division to find which ones actually worked. But yeah, but that's where we first introduced it for this. So now our y-intercept is -1, then it's up 2 over 1. And there's our asymptote. Oblique asymptote. What's our vertical asymptote? Well, we take the bottom, take x cubed minus 1, set it equals 0. X cubed equals 1, cube root it, x equals 1. So there's our vertical asymptote. So now our graph is either going to look like this or like this. It always has to be opposite of each other. So if it's there, it's there.
Oh, okay, I get it.
And that's determined by whatever your x-intercepts are. Once you get your x-intercepts, you plot them, you know exactly where it has to be.
Wait, how do you get rid of the x cubed?
Move me
For
here.
the vertical asymptote?
Oh, here?
Yeah.
Well, if it equals 1, what I would do here, I take the cube root of both sides.
Gotcha, okay.
So the cube root of 1 is 1.
Right.
Why don't I put a plus or minus in front of it? Why does that matter? You're right, but why does that matter?
Not too much for one of the y-axis.
Very good. That's exactly it. Because cubic or odd factors can be positive or negative. Even can only be positive. So that's why plus or minus in there. Good job. No? But you had to, well, you probably, teacher may have skipped it because it's a lot of extra work. Teaching long division is a lot of work. It takes about 2 days past periods to go through and then supplement that with synthetic division. Okay, do you guys want to graph rational functions or wait till next time? This only got 18 pages on it. What time do we get out of here? 12:40? 12:50? 14 minutes? I think we can cover 2 chapters here. No. Okay, let's just kill it here. Time of death.